Hi there, during this session I'm going to be talking about collisions. Specifically I'm going to be talking about elastic collisions, which are commonly used when considering the interaction between particles and the way they collide with each other, and also inelastic collisions, which we more commonly find when things crash into each other in the real world. So let's start off with elastic collisions and see what this means. So, if we think about an elastic collision, we normally consider elastic collisions, or we come across elastic collisions most regularly when we're thinking about particles colliding in a perfect physics model. So what we have here is when I have particles colliding, we normally assume that there's no energy loss in the collision, and therefore the kinetic energy is conserved, as well as the momentum being conserved. So that means that kinetic energy is conserved, therefore the kinetic energy before the collision is going to be the same as the kinetic energy after the collision. So this means we'll often have a formula like this, where we see that u1 is the initial velocity of the first object, u2 is the initial velocity of the second object, v1 is the final velocity of the first object, and v2 is the final velocity of the second object. Now, alongside our calculations for the conservation of momentum, it means we can normally solve for any unknown in this situation. So that's an elastic collision. We also have inelastic collisions. So for instance, with this basketball bouncing up and down, we can see that as it bounces up and hits the ground again and bounces up again, it doesn't reach the same height. And that's because the collision with the ground was inelastic. So some of the energy was transferred and lost to the environment all around it. So let's think about this in details. Kinetic energy is dissipated as heat and sound, so kinetic energy is no longer conserved. But momentum is still conserved. Okay, so if we can remember that momentum is still conserved in these situations, we can still do some calculations. We've got to remember that the majority of collisions are inelastic. The ones which occur every day, there's always some energy, normally heat and sound, lost to the environment around them. The kind of question we often come across is inelastic collisions when things stick together. Okay, so this sticking together question is kind of common. We know that momentum before the collision is going to be equal to the momentum after the collision. This is true, but what we find is the momentum before is going to be equal to mass times 1 times the velocity initial, and the momentum afterwards is mass 1 plus mass 2 times the velocity final. Okay, and this is thinking of a situation when a object hits a stationary object and they stick together. Okay, it'll be more complicated if we have something where we have two objects colliding with each other and then sticking with each other, but it still follows the same set of rules. Now in this situation, we're also going to remember that energy beforehand is going to be half m1 v2 initial, and energy afterwards is going to be half m1 plus m2, because the two objects are stuck together, v2 final plus heat energy, because there's going to be some additional energy, and we normally don't know what that is, so it's very difficult to make further calculations. So that's elastic and inelastic collisions. Let me take you through a problem now. A car of mass 1,000 kilograms is parked on a level road with its handbrake on. Another car of mass 1,500 kilograms travels at 10 meters per second and collides into the back of a stationary car. The two cars move together after the collision in the same straight line. They travel 25 meters before coming to a final rest. Find the average frictional force exerted on the two cars as they become to rest. So this is a very typical inelastic collision situation where two things have stuck together. Now, to get to the final answer, you've got to go through multiple steps. So try and go through these multiple steps, and then let me take you through what you need to have done. First of all, use the principal momentum conservation to find the speed of the two cars immediately after the collision. So total momentum beforehand is 1,500 times 10. If the speed after the collision is v, then we can work out v to equal 6 meters per second. So we know the velocity after the collision. Then after that we can think about using the idea of work done by the frictional force and bringing the car to rest will equal the loss in kinetic energy. That seems to make sense. Okay, so that means the energy lost will be from the initial kinetic energy down to 0 when it comes to a halt. So the kinetic energy of the two cars immediately after the collision is going to be given by half times 2,500 times 6 squared, which gives me 45,000 joules. I need to work out what the average frictional force of the car acting in the car as work done. Now, because I know that it took 25 meters for all this kinetic energy to be dissipated, it means I can work out that the average frictional force is going to be 1,800 meters. So there's a typical question. Now remember, as long as you recognize the difference between inelastic and elastic collisions, this is always going to be a situation where you're going to plug in and playing and trying to find the unknown. So good luck with that in the future.